Okay, let's try this again. So, the kidney is all about filtration. That's its big thing is to filter nutrients and things either back into the blood or into the urine. Filtration it occurs primarily in the renal corpuscle or in the renal corpuscle, which consists of the glomerulus and the Bowman's capsule. Filtration membrane has three layers. The first membrane, the first layer of this membrane is fenestrated. Is the fenestrated capillary epithelium. These have large pores which allow water and small solutes back through, but they block blood cells. Two, we have a basement membrane. Basement membrane. The basement membrane is negatively charged and it repels most plasma proteins. And three, we have the podocyte filtration slits. Um, these are these are processes with slits. Um, processes with slit diaphragms that provide the final size selective barrier in the kidneys. The things that get filtered in here, we will have water gets filtered, ions like potassium, um, chloride, calcium, that kind of stuff. Um, Also, we'll have glucose is filtered here, amino acids, vitamins, urea, and small peptides. Now, I'm just gonna say those ones, but things that don't get filtered are things like cells. They're not filtered here. Most proteins are not filtered here. Some are, but most are not. And then protein bound substances are not filtered here as well. Filtration is governed by the net filtration pressure, or the NFP, net filtration pressure. Um, is the balance of a few different things, like GHP, or the glomerular hydrostatic pressure, is the blood pressure pushing fluid out of the capillaries. It's around 55. It's around 55 millimeters of mercury. And then the CHP, or the capsular hydrostatic pressure, is the fluid pressure in the Bowman's capsule that's resisting filtration. It's around 15 millimeters of mercury. And then we have the BCOP, which is blood colloid osmotic pressure. And this is the osmotic pull of plasma proteins that oppresses filtration, which is about 30 millimeters of mercury. So NFP is equal to GHP minus CHP minus BCOP. And this pressure determines how much filtrate is being produced. Okay. Um, Now, we do need to regulate blood flow in the glomerulus. And we have afferent and efferent arterioles that control the flow and pressure in the glomerulus. The afferent arterial dilation. Afferent arterial dilation will increase GHP and thus increase filtration. The afferent arterial constriction will decrease GHP and thus decrease filtration. The efferent arterial, I'm doing that word. Sorry. Efferent arterial constriction will increase GHP, and then increase filtration. The afferent arterial dilation will decrease GHP and decrease filtration. The two intrinsic mechanisms that can maintain the GFR rate so these two intrinsic mechanisms will maintain GFR despite the blood pressure changes. So these two mechanisms are myogenic mechanisms, which is smooth muscle of the afferent arterial constricts when stretched. And then also the tubulo-glomerular feedback, and we're going to talk about that in a second. Okay, let's go more into GFR. GFR is the volume of filtrate that is formed each minute. A normal amount is around 120 milliliters a minute, and it reflects how well the kidneys are filtering blood. Clearance describes the volume of plasma that's cleared of a substance per minute. If a substance is freely filtered and neither secreted nor reabsorbed, its clearance equals the GFR. So inulin is the gold standard. It's not metabolized, it's not secreted, it's not reabsorbed. And creatinine is also commonly used clinically. It slightly overstimulates GFR because a small amount is secreted, but it's acceptable and it works. So, clearance is equal to the urine concentration times urine flow rate divided by the plasma concentration. Like I said, if clearance, if something is freely filtered and it's not secreted or reabsorbed, then clearance is going to equal GFR. Okay, now let's go into what happens inside of the kidneys in terms of reabsorption. So after filtration, the kidney reabsorbs most water and solutes that will prevent loss of essential substances. So general mechanisms, reabsorption occurs. It occurs via like primary active transport, so like the sodium potassium ATPase, and secondary active transport, which is like things like glucose and amino acid being co-transported with sodium. Diffusion and facilitated diffusion, like chlorine following sodium, and osmosis, which is water following the solute movement. So, major substances are things like sodium. Sodium reabsorption will drive a lot of these other processes. In the proximal tubule, sodium enters by cotransport with glucose. amino acids and phosphates, and by sodium and by the sodium uh, hydrogen exchange. A sodium potassium ATPase on the basolateral side will pump sodium into the blood. So that's one major solute. Another major solute is glucose and amino acids. Glucose is reabsorbed almost entirely in the proximal tubule, and it uses sodium coupled secondary transport to do so, and it leaves the cell by facilitated diffusion into the bloodstream. If blood glucose levels exceeds about 180, then the transporters are saturated, and then the excess glucose remains in the filtrate and will be released about in the urine. This is a sign of diabetes because your blood sugar is so high that the transporters are saturated and can't reabsorb glucose anymore. Okay, another one is chloride. Chloride will follow sodium by electrical attraction or by solvents drags. Later, in the later nephron segments, you will use chloride channels as cotransporters. Okay, and water is reabsorbed by osmosis as solutes move. The proximal tubule, as we're talking about here, is highly water permeable. The collecting duct is also permeable depending on ADH. So if ADH is present, then it is permeable. If it's not, then it's not permeable. Another one is potassium. It's mostly secreted in the proximal tubule and the loop of Henle. And it's also secreted in the distal nephron under the influence of aldosterone. Calcium is reabsorbed in the proximal tubule and the distal tubule. And the distal tubule uses active transport mechanisms regulated by the parathyroid hormones. Okay. Now I want to talk about RAS, RAAS, or renin angiotensin aldosterone system. This is triggered by low blood pressure, or low sodium chloride, or sympathetic activation. So what happens is, number one, has to do with renin. Renin from the juxtaglomerular cells is converted into angiotensinogen, which then goes to angiotensin 1. I'm just going to skip. Angiotensin 1. And then ACE converts angiotensin 1 into angiotensin 2. Angiotensin 2 is very useful. It will constrict arterioles, which will increase GFR. It also stimulates aldosterone release. It also increases thirst and ADH release. We mentioned that angiotensin 2 will stimulate aldosterone. Aldosterone has a lot of cellular effects as well. It affects the distal nephron and the collecting duct. It will also increase the expression of the ENaC channels and the sodium potassium ATPase. So the result from this is we have more sodium being reabsorbed, more potassium being secreted, and water will follow sodium, which increases the volume of the nephron. Now, we also will be producing ADH at this time when we release angiotensin 2. ADH will insert aquaporin channels into the collecting duct, and this will allow more water to be reabsorbed, and the urine becomes more concentrated. Without ADH, collecting ducts are water impermeable, and this will dilute urine. Okay, last but not least, we're going to talk about the loop of Henle and the medullary concentration gradient. The loop of Henle establishes the medullary gradient. So in the descending limb, is permeable to water, so water can go in, but it is not permeable to solutes. Water will leave the hyperosmotic medulla, and the filtrate becomes more concentrated. In the ascending limb here, it's impermeable to water, and it actively pumps sodium potassium chloride out via the NKCC transporter. The filtrate becomes more dilute as the solutes leave, but the water does not. This countercurrent interaction, it multiplies the small differences in the strong osmotic gradient. And it can go up to around 1,200 milliosmoles. Now, on the other hand, when ADH is hot, collecting ducts become now permeable to water. Water moves out into the medulla, and the urine becomes concentrated. When ADH is low, the collecting ducts remain impermeable, and water stays in the tubule, and the urine is dilute. Thus, the kidney can produce urine anywhere from 50 milliosmoles, which is very dilute, to 120 milliosmoles, which is very concentrated, depending on the hydration status, and ADH. This is also where urea comes in. If urea is found here in the loop of Henle, then that causes higher concentration and water follows. Okay, that's pretty freaking good.